Hello my dear friends, I really hope that you are doing great. Welcome to our today's class. It's our third lesson on the fourth topic of Form 3 work, which is called Work, Energy, Power and Machines. As it is our norm, let me start by giving you the quote of the day, which states that our future is bought or sold by the choices we make today. We shall discuss that quote at the end of our class today. So today we are basically looking at the potential energy and the kinetic energy in details. So we are saying that an object in a raised position possesses what we call gravitational potential energy, which is given by the formula potential energy, or the gravitational potential energy, is equals to the mass of the body multiplied by gravity on that particular planet. For example, on Earth, the gravity is either at 9.8 Newton per kilogram or 9.8 meters per second squared, or it can also be given by 10 Newton per kilogram or 10 meters per second squared. Therefore, for a body to be said to possess what we call gravitational potential energy, that particular body, it must be at some raised position, or there must exist some height of that particular body from the ground. Otherwise, if the body is resting on the ground level, it means the height from the ground level will be 0, and therefore mass times gravity times 0, the final answer will just be 0. Therefore, a body is only said to possess gravitational potential energy, 1, if it has some mass m, and 2, when it is at some height, or some height from the ground. For example, the height, maybe you can just give an example of maybe a mango which is resting on a tree, maybe which is something like maybe 3 meters from the ground level. Therefore, in that case, the 3 meters will be your height of that particular body from the ground. Then the mass of the mango could be maybe something like 20 kilogram. Then gravity on Earth is always either 10 or 9.8 Newton per kilogram. Therefore, the gravitational potential energy possessed by such a body will be given by the product of its mass, gravity, and the height of that particular body from the ground level. The same another very good example whereby gravitational potential is applied in real life situation is in dams. Yeah, you find water which is resting in a dam. Then the dams are always constructed in such a way that they are at some raised position from the ground level. So the reason for raising that particular height is simply to increase this particular height, because the larger the height of that particular body from the ground, the greater the gravitational potential energy. Therefore, that gravitational potential energy is usually converted to kinetic energy, that is in dams through the waterfalls, which is used to turn some turbines, which in turn they cause a conductor to rotate within a magnetic field. Hence, hydroelectric power is actually produced. So we can also have such an example whereby gravitational potential energy is applied. For example, I'm sure you have seen tanks. Tanks are usually raised at some higher positions from the ground. For example, a tank that is supplying water in maybe in a school, or a tank that is supplying water maybe in a house. The tanks are usually placed on the rooftop of such high buildings, or on the rooftop of maybe your school building. So the reason for placing those particular tanks at the rooftop is that they are trying to increase the height, because when you increase the height of the body from the ground level, then that particular body is at rest. You are simply increasing the gravitational potential energy, because when the height is large and also that particular water has some large mass, then you multiply it by gravity, it means the gravitational potential energy is actually great. And remember, when that water flows from that particular height, that is from the raised position, all the gravitational potential energy will actually be converted to kinetic energy, that is energy in motion. So the larger the gravitational potential energy, the larger the kinetic energy that will be produced. Because remember that you can never create nor destroy energy. Instead, you can only change it from one form to another, as we saw in our previous class. So the reason for raising the tanks above the ground is simply to increase the height, hence increasing the gravitational potential energy, which is in turn converted to a larger kinetic energy, actually, which provides the pressure with which the water comes through the water taps in your rooms. Then the work done in compressing or stretching an elastic material. An elastic material are those materials which behave like fully stretched elastic skins. For example, we have a slinky spring. Yeah, we can also have a rubber band. So the work done in compressing or stretching an elastic material, for example a spring, is equal to the energy stored in such an elastic material. So this energy, we call it the elastic potential energy. So basically you are saying that we have two main types of potential energy. One, we have the gravitational potential energy. Then two, we have the elastic potential energy, which is simply the potential energy which is stored in elastic materials. Then we have said that the work done, that is the work done in compressing or stretching an elastic material, that particular work is equal to the energy stored in such an elastic material. Remember also the SI unit for energy and work done are just the same. That is the joules or the Newton meter. So from this particular statement, we are simply saying that the elastic potential shall be given by, or we can also have this, that a graph of force against extension, that is for an elastic material, is a straight line graph from the origin, the way this particular graph is here. So if you plot a graph of force F against extension for an elastic material, for example a spring, as we saw in the Hooke's law, that particular graph will be a straight line graph through the origin. Then we are saying that the elastic potential energy in this case shall be given by the work done in stretching that particular spring. Then earlier on in our previous classes, we did say that the work done, that is the area under a force extension or under a force distance graph, will always give you the work done. Therefore, the elastic potential energy will be given by the work done in stretching the spring. And we are saying that work done is equal to the area under a force distance graph or a force extension graph. Remember, the extension in this case is what is representing our distance. Therefore, if we look at this particular shape, remember the work done, that is the area under the curve, is simply the area between this particular vertical line, that is the line of our graph, and the that is the horizontal axis, which is the extension axis. Therefore, the shaded area, this is the area under this particular graph of ours, which is the force extension graph. So this will be given by, remember the shape is in form of a triangle, that is a right angle triangle having its 90 degrees here. Therefore, the work done will be given by, or it will be equal to, the area under a force extension graph or a force distance graph. Then in this case, the area is the area of a triangle, which is a right angle triangle, which is given by a half base times height. But in this case, our base is E, that is the extension, then our height is F. So remember, the height is actually F, then the extension, which is our base, is actually denoted by E. Therefore, the area is equal to a half base times height, which is a half. Our base is extension, the height is force. Therefore, a half base times height, or force times extension. But from Hooke's law, we did saw that force is equal to Ke, where K is the spring constant and E is the extension, and of course F is the stretching force. So if I substitute force is equals to Ke, that is where I have F, I just want to substitute with Ke. So I'll have the elastic potential, which is equals to the work done in stretching the spring, being equal to a half times F. Remember, F is Ke multiplied by the E that had remained here. Therefore, E times E, you will get extension squared. Therefore, the elastic potential shall be given by the formula a half K times extension squared, especially for the case of a spiral spring. Next, we look at kinetic energy, and we are saying that an object in motion possesses kinetic energy, which can be of two types. One, we have what we call rotational kinetic energy, also called the circular kinetic energy. Yeah, when a body is rotating, for example, there is a way in which you can hit a ball in such a way that it rotates through the same area. So such a ball, or even a marble, it possesses what we call rotational kinetic energy or circular kinetic energy. The other type of kinetic energy is what we call translational kinetic energy. The other term for that is linear kinetic energy. So this is simply the kinetic energy possessed by a body moving in a straight line. Remember, linear means moving in a straight line, or linear simply means in a straight line, then motion. So when we talk of linear motion, it's simply motion of a body in a straight line. Therefore, the kinetic energy possessed by a body moving in a straight line, we call it translational kinetic energy, or simply linear kinetic energy. So such kinetic energy, or the kinetic energy, is given by the formula a half multiplied by the mass of the body times the square of the velocity at which that particular body is moving. Then the work done by the force, that is the work done by the force to move a body from one state of kinetic energy to another state of motion, or to another state of kinetic energy, is always given by the kinetic energy gained or kinetic energy lost by the body. Remember, if a body is accelerating, in such a case, the motion of a body will be increasing with time, and therefore the final velocity will always be greater than the initial velocity. So if a body is accelerating, then in that case there will be gain in kinetic energy. But if a body is retarding, or if a body is moving with a decreasing velocity or with decreasing speed, then such a body is said to be losing kinetic energy. Therefore, in such a case, work done will be given by that is the loss in kinetic energy, or kinetic energy lost by the body. Then the work done and the kinetic energy gained or lost by the body will be given by a half mass of the body times the square of the final velocity of the body minus a half times the mass of the body times the square of the initial velocity of such a body. Remember that if there is gain in kinetic energy, final velocity will always be larger than the initial velocity. Therefore, you will obtain a positive value for the work done by the force. But if a body is losing kinetic energy, or if a body is decelerating or retarding or moving with a decreasing velocity, then in such a case, the initial velocity will always be larger than the final velocity. Therefore, for a body that is decelerating, it will experience loss in kinetic energy, and if you find the difference between a half mv squared minus a half mu squared, in such a case you will get a negative value. So the negative is simply used to denote the loss in kinetic energy, but a positive value simply shows you that there is gain in kinetic energy. Next, we look at a few examples involving such formulas. So question 1, we have that a body is acted upon by a varying force F over a distance of 4 centimeters as shown. Sorry, this should be 4 meters. Over a distance of 4 meters as shown below. So we are required to calculate the work done by the force. Calculate the work done by the force. So you have just said that the work done is equals to the area under a force distance graph, or also the area under a force extension graph for a body experiencing, that is elastic potential energy. But for a body experiencing for a body experiencing gravitational potential energy, the work done will be force times the distance, which is just mgh. Therefore, work done is equals to area under a force distance graph, which is equals to, in this case, we have two areas. Remember, the area is always that is the area, or the region between your graph and the horizontal axis. The horizontal axis in this case is the distance axis. Therefore, the area under this particular force distance graph will be given by area A, which is shaded, and also plus area B. So if we observe area A, it is triangular in shape. Also, area B is in triangular in shape. So we know that area of a triangle is given by, that is, so the total area will be given by area A plus area B, which is equals to, area A is in form of a triangle. So area of a triangle is a half base times height. So this shall be given by a half base. Base is actually the distance, that is the distance from here up to 3. Then the height, of course, will be 4. So you just draw a perpendicular bisector here, or a line that is perpendicular to the horizontal axis to give you the height of that particular triangle. Then plus a half base times height. The base for body B will be 3, the distance from 3 up to 4. Then the height will be this particular vertical distance here, which is also 4 Newton, or negative 4 Newton. But remember, when we are calculating the work done, we actually ignore the negatives. We are only interested with the total area. So remember, the area for part B, because it is below the horizontal axis, the area will be negative. But when you are finding the work done, we ignore the negative. We just take the area to be positive. Therefore, the work done will be given by the area A is a half base. The base is the distance from 0 up to the 0 up to 3. So the base is that is the base is D, then the height is F. Therefore, work done is equals to FD. That is a half FD. So the force for this particular case is 4 Newton. That is for triangle A. Then the base is from 0 up to 3, which is just 3 minus 0, which gives you 3 meters. Then plus the height for this particular case is the distance from here, the force from here up to the vertical position, that is 4. And you have said that when you are working for the work done, you ignore the negative. So you just take, we are only interested with the magnitude and not the, that is the direction. We are only interested with the magnitude or the size of that particular force and not the direction in which that force is acting. Therefore, our height is 4 Newton, then times the base. The base of triangle B is 4 minus 3, which gives you 1 meter. So if you take a half times 4 times 3, you will obtain 2 goes into 4 2 times 3, you will get 6. Then a half times 4 times 1, 2 goes into 4 2 times 1, you will get 2. Remember, we were to get -2, but we are saying that for work done, we are not interested in the direction. Therefore, we just take the magnitude. That's why I've taken this one as +4 instead of -4. So whenever you are doing questions involving work done, just ignore the negative. We only concentrate with the positive values. So this shall give you 6 plus 2, which gives you 8 Newton meter. But remember, 1 Newton meter is equals to 1 joule. So this can as well be represented as 8 joules. Then part B, that is question 2, reads that a car traveling at a speed of 72 kilometers per hour. So remember, 72 kilometers per hour, this is the initial velocity. Therefore, U is equal to 72 kilometers per hour. To convert into SI units, which is the meters per second, we simply convert kilogram into meter. We know that 1,000 meters is equals to 1 kilogram. What about 72 kilograms? So you'll have 72 kg divided by, that is kilogram over 1 kilogram times 1,000 meter. Then we know that 3,600 seconds is equals to 1 hour. What about 1 hour? So we'll have 1 hour divided by 1 hour multiplied by 3,600 seconds. So this will give you your initial velocity as 20 meters per second. That is in SI units. Then is uniformly retarded. So to retard simply means the body is moving with a decreasing velocity, or the body is decelerating. Is retarded by application of brakes and comes to rest. If the body is coming to rest, that one simply means the final velocity is 0 after 8 seconds. So that is time 8 seconds. So part A, if the car with its occupants has a mass of 1,250 kg, calculate part A, the braking force. Now we know that from Newton's second law of motion, we know that force should be equal to ma, that is mass of the body times the acceleration. We are given the mass of that particular body, but we don't have acceleration, but we are given u, v, and t. Therefore, we first of all find our acceleration, which is equal to change in velocity over time. So v minus u over time. So final velocity is 0 because the body was coming to a state of rest, that is after the motion. So final velocity is 0 minus initial velocity, which is 20, divided by time is 8 seconds. So this gives you acceleration of negative 2.5 meters per second squared. So as you can see, acceleration is negative, simply meaning that the body is decelerating or it is moving with a decreasing velocity. Therefore, force is equal to ma. So mass of the body was 1250 times acceleration of negative 2.5. So this gives you a force of negative 3,125 Newton. So also remember, the force is negative because it is a braking force, or it is a force that is causing a deceleration, and therefore the force that is applied on the brakes is always in the negative direction. That is, to understand this, just go and revisit where we explained the working of car braking system. You realize that if that is, the force is always applied in the opposite direction because it is trying to retard or to cause that particular body to decelerate. Therefore, the force is negative. So the braking force is actually, the braking force is equals to the retarding force, which is equals to 3,125 Newton. So the negative is just to show that the force is being applied in the negative direction or in the opposite direction, or to show that the force is a retarding force or a braking force. Therefore, our braking force will be 3,125 Newton. Then part B, we are required to find the work done in bringing it to rest. Remember, work done, because this is, the body is moving, it means the type of energy involved is kinetic energy. Therefore, work done shall be given by, is always given by either the gain in kinetic energy or the loss in kinetic energy. But because the body is retarding, it means in this case the kinetic energy will be lost because the body is losing its motion. But if the body was accelerating, the work done will be equal to the gain in kinetic energy. So gain or loss in kinetic energy is given by a half mass of the body times the square of the final velocity minus a half mass of the body times the square of the initial velocity. So the mass of the body we were given as 1250, initial velocity, no, final velocity was 0 because the body was coming to a state of rest. So a half times 1250 times 0 squared minus initial velocity was 20 meters per second squared. So we just substitute the values. So you compute the difference, you will get 0 minus 250,000 joules, which gives you a work done of negative 250,000 joules. So the negative is because it's simply to show that kinetic energy is lost. Kinetic energy is lost. So actually the negative is just to show that the kinetic energy is lost. Otherwise, if you get a positive value, that one simply tells you that kinetic energy is gained. So in this case, the final answer for the work done is simply 250,000 joules, 250,000 joules. I also have an exercise here that I do recommend you should try at your own free time to gauge whether you have understood the examples that we have just done. And in case you have any challenges in handling any of the question, just feel free to drop a comment specifying the specific question that you need help in. And of course, as always, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that our future is bought or sold by the choices we make today. So the quote is cautioning us to be very careful about the choices we make today because those choices will have long-term consequences. So these choices include the type of people we choose to surround ourselves with, the type of information we choose to feed our minds with, and the amount of time we choose to allocate for doing activities that lead to self-growth as opposed to the amount of time that we choose to allocate in doing activities that lead to self-entertainment without self-growth. And lastly, remember that just in the same way a candle can wipe out darkness from a room, also one correct choice can change your whole life. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will be notified. If you know any student or anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy. Thank you very much. Until next time.